So one last conversation to finish the puzzle about how much resistance a particular piece of wire offers in a circuit is a temperature coefficient. So here we are, lesson 13. This is a really short PowerPoint, but it's kind of a tricky piece of math because there are 3 steps involved. There is, and in other electrical courses, you may be introduced to a single equation that can get you from the start to finish in a single step. But I don't feel that equation offers any understanding about what happens. Okay, you're just plunking numbers into the equation and bam, the equation gives you an answer. The process that I'm going to show you, going through the 3 steps, really helps you see how it is that we get from start to finish in terms of understanding the resistance and how the resistance of a piece of wire changes with temperature. Okay, so first of all, the temperature coefficient itself is a number. It's a multiplier. Okay, so let's look at that temperature coefficient. So, okay, well, let's start the conversation here with the fact that when computing wire resistance, we always start at 20 degrees. So you've already seen that, right? When we looked at the specific resistance of copper and the specific resistance of aluminum, we talked about that being the resistance of the piece of wire at 20 degrees. Okay, so that's a starting point. But typically, that's not going to be the temperature. That's roughly room temperature, but there's all kinds of reasons why the temperature might be much lower or much higher in the actual environment that conductor is being used. So we have to compensate for these changes in temperature. So the temperature coefficient does that for us. Here's the number. Okay, copper has a temperature coefficient of 0.00393 ohms per degree Celsius. Wow. Or, here we go, 0.393% per degree. Okay, so I want to talk about the percent per degree because it kind of helps us a little bit more understand, okay, what this is all about. But it's the first number. It's the 0.00393, which is the number that we must use when we do the math. Okay, but when we take a number and we change it into a percentage, it just means we're moving the decimal place 2 spots. And so we end up with the number 0.393% per degree Celsius. What that means is that the resistance of that copper, any copper, is going to change by 0.393% for every degree the temperature changes. Okay, and in fact, it is an increase. It's a positive change, which means as the temperature goes up by a degree, the resistance goes up by 0.393%. Okay, let's back up to the first number though, which is not a percentage. It's ohms per ohm per degree, which means the resistance of the copper will change by 0.00393, okay, ohms. It changes by that much for every ohm of resistance that conductor is already offering in the circuit, and then by every degree that the temperature changes. Wow. Okay, we're going to do some math on this in just a moment, but let's look at aluminum as well. And aluminum is a slightly less ugly number and just slightly bigger. Okay, so for every degree that the temperature changes, aluminum changes by 0.4%. Okay, which means 0.004 ohms per ohm per degree Celsius is the number that we will use in our equation. Okay, so aluminum changes in resistance a little bit more every degree as the temperature changes than is true for copper. All right, let's try to do some math on this. How do we go about calculating temperature coefficient? Calculating changes in resistance. Here are the 3 equations, so let's look at them. First thing we need to figure out is what is the change in temperature. Okay, so this triangle in front of the T, we call this delta, and delta T, delta anything means the change in that thing. Okay, so delta T represents the change in temperature. All right, and we calculate delta T by taking T2 which is the final temperature, and subtracting that from T1, which was the initial temperature. Now it's important that we do it in this order to get our positive and negative signs correct so that we can figure out whether the temperature is going up or the temperature is going down, because ultimately that's going to decide whether the resistance goes up or goes down. Okay, so for example, if the temperature goes up, T2 will be a bigger number than T1. The higher temperature is the final temperature, which means when we subtract T1 from T2, we end up with a positive value, and a positive value for the change in temperature means the temperature went up. Okay, so that's where we start. We have to calculate delta T. How much did the temperature change? Okay, that will allow us to calculate delta R. So this is the second equation, the second step. How much does the resistance change? And delta R is equal to T subscript C. That's the temperature coefficient. So now we need to know whether we're talking about copper or whether we're talking about aluminum. What is the value that we're going to have to put into our equation? Okay, and remember, this is not the percent number. This is the number that has the extra 2 decimal places. Okay, so the temperature coefficient multiplied by the change in temperature, multiplied by whatever the resistance was of that conductor at the original temperature. So that's R subscript T1. If I get my pen out here. Okay. Oh, that's my highlighter. That'll work. R subscript T1 this is what I'm looking at right here. This is the resistance of the conductor in the first place. Okay, so in our first examples, this is going to be at 20 degrees. Okay, because that's the task. First of all, we figure out the resistance of the conductor at 20 degrees. That's the previous lesson. And then we're going to use the temperature coefficient to find out what the resistance change is going to be as a result of the change in temperature. Okay, so that's the second step. We need to know what the change in resistance is. So here's where the positive and negative value of delta T comes into effect. If delta T is positive, if the temperature went up, then all of this will be positive and delta R will be positive. Okay, the resistance will go up. But if delta T is negative because the temperature went down, then delta R will be negative as well. Okay, so that's the second equation. And then finally, the third equation, once we've gotten this far, is pretty straightforward. The question is, what is the resistance at temperature 2? Well, it's equal to the resistance at temperature 1, where we started, plus the change in resistance. Okay, so we're adding delta R, and if delta R is positive, then we get an increase, and if delta R is negative, then it will be the resistance of the original temperature minus the change in resistance. And that gives us our final resistance, the resistance of a conductor at temperature 2, after the change has taken place. All right, so that's the equation. The 3 equations, that's the process. Let's put some numbers to it. We have a length of copper wire, and we calculated, okay, that the resistance is 125 ohms at 20 degrees Celsius. Okay, these aren't very realistic numbers, but a nice place for us to start, practice the math. Okay, 125 ohms at 20 degrees Celsius. So that was calculated from the size of the wire and the specific resistance of copper. Okay, gets us to this point. Now the question is, what would be the resistance of the wire if it was installed in an area at 60 degrees Celsius? So this is kind of a realistic scenario, if not the numbers for the conductor, at least the idea that what happens if we install these wires, you know, in an environment where it's always extremely hot. Okay, instead of nice comfortable room temperature 20 degrees, it's always 60 degrees in this room. Okay, what's going to be the effect on the conductors and our electrical circuit? So step 1 is to figure out the change in temperature. So it's T2 minus T1. So we want to talk about a situation where the ambient temperature is 60 degrees. So we take the 60 and we subtract from it the 20, which is where we began. That's how we calculated our resistance in the first place. And that gives us a delta T of 40 degrees. Take that 40 degrees and take it to our second equation, which says let's calculate the change in resistance. as a result of this. So look at TC. So the temperature coefficient for copper is 0.00393, right? That's the number we have to use. We can't use that percentage number, okay? Multiplied by the 40 degrees Celsius, the change in temperature, multiplied by 125 ohms, which is what we were told the resistance of the wire was originally in the 20-degree environment. And the answer we get is 19.65 ohms. So that is how much the resistance changes when we compare the 60-degree scenario to the 20-degree scenario. And so then the question is, what is the actual resistance of the wire at 60 degrees? And the resistance at T2 equals the resistance at T1 plus the change in resistance. So we started out at 125 ohms. We have to add the 19.65 ohms so that the resistance of the wire in this 60-degree environment is 144.65 ohms. Okay, let's try it again. Because I know this is it's going to just repetition to get this to sink in. I know at first glance this is ugly, but once you work through it a few times, things sort of fall into place. What do we have here? We have aluminum wire, resistance of 50 ohms at 20 degrees Celsius. So there's what we calculated originally. Now the question is, we place this in an area at 0 degrees Celsius, what will be the resistance of that conductor? So first of all, what is the change in temperature? Well, the change in temperature now is going to be minus 20 degrees Celsius because we've gone down from 20 degrees to 0 degrees. So we must carry that negative forward to the next equation, where delta R equals temperature coefficient times the change in temperature times whatever resistance we started with. So notice now this is aluminum, so the temperature coefficient is 0.004 multiplied by negative 20 degrees multiplied by 50 ohms, the resistance of that conductor initially at 20 degrees. And the result is a drop in resistance, a negative delta R of negative 4 ohms. So let's take that negative 4 ohms, apply it back to the original resistance of the conductor. The resistance at T2 equals the resistance at T1 plus delta R, which is 50 ohms, which was what we were told it was at 20 degrees, plus minus 4 ohms, which means 50 minus 4, which gives us an answer of 46 ohms will be the resistance of that aluminum conductor at 0 degrees Celsius. Okay, there's a couple of examples walking you through the steps. I'm going to put the next exercise sheet on Blackboard. Continue to just practice this, try to work your way through it. This one, like I say, it looks a little bit ugly at first, but once you've done it a few times, I think it sort of starts to make sense. I hope it does. Okay? There's where I stop this one. That's the end of this lesson. Go and print off that exercise sheet and start crunching some numbers.